preliminary analytic result is from Mahata City. You see by Central Petroleum Laboratory, Ministry of Energy and Mining, and Department of Physics, Forest of Science, Ethiopia University. So, what I would like to convince you with is, we wish to make a lab name, laboratory name, of meteorite we have in Mahata City, in Nubian Sahara, North Sudan. Okay, what's the approach? The approach is petrographic thin section, XRD analysis, chemical analysis, especially atomic absorption, and then after that, comparison of the laboratory results from above mentioned to previous work. So we start to analytic procedures. We use a nuclear microscope, vacuum impregnation units using blue light resin, since the rock we have seen from meteorite is disintegrated, polarizing microscope, reflective light, XRD chemical analysis. Okay, we started for binocular microscope. We use for purpose of isolating small crystals or mineral grains to determine and to know what type of thin section we can start the grains. So what we have is one of the meteorite samples, chip samples for the binocular. So you can see different type of illuminating. You see colors, white, reddish. So we wish to start the thin section after that when we get the thin section after the binocular. It's like same. So we started for polarizing microscope for in and out. We prepared a thin section by Asteroid machine after impregnation by blue dye resin because the sample was fragile and cracked. Then it composed mainly what we have seen silicate minerals, mainly olivine. Then after that, as a modeling, petrographic modeling, we have yes. We have silicate minerals of olivine. After that, zoned and non-zoned pyroxene twin, and some iron oxide, and few viscosity matriculates. So you see some of pyroxenes. You see zoned and non-zoned. You see, this is blue is design to fit the. You see, and most of these thin sections you see, for all of these are olivine. You see, olivines. But if you see here, it's a zoned pyroxene. Most of the, you see. And here you see, when we wish to say, for example, this is the corner, we have some zoned pyroxene. We can say, you see J, you see HJ 14, 15. Okay. And after that, since we know what type of olivine, what type of pyroxene, we use it XRT. Mineralogical. So XRT results confirm the occurrence of magnesium olivine, and since it's the first part. And then orthopyroxene, which is N-state, which mainly occur in the meteorites. So a few amount of particles, mostly calcium. I don't know whether it's a levolite or anorthite, but it's more calcium. Okay, this is the XRT. If you look here, bulk 1712 meteorite. This is the number of lab number, but I never use it. The number of Department of Physics for this, I don't know. We ignore it mostly because the laboratory it's a national laboratory. We never use the number of the
You have to, because otherwise you can't keep.
Yes. This is the secret. The secret. So this is 172. It's a commercial work. So we never use. Okay, this is our number. So if you see the magnesium iron silicates 64.8%, is very high. Then after that we have iron alpha 8% and calcium magnesium carbonysilicates 27%, which is confirmed same as we have seen for petrography. So after that we go reflected light microscope, because we used to determine iron oxides, because we never use polarizing microscope and binocular, you can never detect iron oxides. So that we using this type of microscope. Okay, the light, you see the white color is mostly iron oxides. And you see, it's not like very white, it's a little white, it looks like nickel, I don't know, but it's some of oxides. Okay, after that, we go to the chemical analysis, oxides and native elements. So this is a native elements, mostly weight percentage calcium, chromite, ferrum, magnesium, and cobalt, aluminum, nickel, and chalcophyte for the silver loving, which is important to determine meteorite for ppm. Okay, at last, we done comparison between chalcophyte elements in chondrite meteorite, which is already known in table 1, and Manhattan sample table 2. So you see, this is from afterwards and Kelvin 1988, which is known. So as a reference, if you look cobalt, it's not like the standard, but all zinc, arsenic, tin, and antimony, you see it's a more or less same, similar, about similar, you see. For example, zinc 17 up to 312. Here you see 109. Arsenic 1 up to 4. Here we have less than 3 possible. If you antimony 0.71.8, less than 1. Tin 0.06 up to 0.2. The limit we have 0.4, which is really, if you compare to each other, you can say it's similar. Okay, we have done another comparison between tin sections with or without contour structure, because most of the chondrite, stony meteorite chondrite have something like this structures, which is rounded particles. These rounded particles, we will never get all the tin sections we have in Manhattan. That's why we can conclude this preliminary result is not last result is, we can conclude this remark. The lack of contour structure, petrographic analysis in all the samples show the samples from stony meteorite and chondrite type. It's from stony meteorite and chondrite type. Although results from atomic absorption, chemical analysis indicate more or less similar concentration of the chondrite type. We recommend to conduct additional fieldwork and analytical tests, XRF, the atomic absorption, XRT, and petrographic sections in order to explore more about how to see the meteorite. Thank you very much. Any comment, any question?
Thank you. That's very important work. It's almost the first thing that needs to be done to characterize the pieces, the similarities and differences among them, and among the other comparisons to the other meteorite types. My question, it wasn't clear, the comparison sample that you used from Warren and Calamine, Was that a carbonaceous chondrite or an ordinary chondrite?
It's a good question. That's why I say we need to do more because I'm geologist.
Right, exactly.
Yes. But what I know is the shape, the chondrite structures, mostly we will get in chondrite, not a chondrite.
Right. Okay. But among the chondrites, the meteorites that have the chondrules, the round.
Yes, yes.
There are two types. There's carbonaceous chondrites and there's ordinary chondrites. And I know in the paper where you got the numbers, they say what kind and the name. And in the meteorite community, the name and the type is very important. And soon you will understand, you will experience the need for more specific names of the meteorites.
Yeah.
No lab number.
So since I am not a specialist for chondrite, we need to work together to know what type of chondrite.
Right. And now you're an expert on Alamanda.
Okay.
Yes.
I'm a neurologist. Thank you.
So you did atomic absorption spectroscopy on these meteorites? How did you extract the minerals to measure them?
Oh, this is a technician work. I don't know.
Oh, okay.
Any further questions? Thank you very much.
Thank you very much.
Thank you very much. This ends the official section on the meteorite properties, and we are now heading into the session on the origin of 2008 TC3 and the dynamics. So we're going back from geology to astronomy. And I have one presentation that was sent to me last night by Paul Chodas, who was one of the people that couldn't come, begging me to please present it. So I'll show a few of his slides, because I think it does introduce the story by Jeremy and Francois. Let's see. So Paul Chodas is working with Steve Chesley, and he was one of the people that analyzed the trajectory of 2008 DC3, helping to determine where exactly it landed. And Paul looked at where the asteroid might have originated, but he didn't go back very far in time. And Jeremy did went back a lot further, and so that's why it's nice to show this as an introduction. These are all the asteroids that are bigger than 1 kilometer that can come close to the Earth. So these asteroids move in eccentric orbits, and they are found everywhere in the inner solar system, but this is how they move. So they go in these eccentric orbits. And then we'll skip all of that. This was the trajectory that was calculated, and I thought this was neat too because it shows where the object was discovered. So this is the orbit of the moon. So here's the Earth, orbit of the moon, this is where it was found. So it was really coming in, and then hitting its...
Peter,
no?
I have to ask you to go back to the first slide and let people look at it a little longer.
Sorry, which
Because
one?
maybe they're not used to looking at, or the one before that. Okay, now,
Yes.
please, what are the red circles?
Okay. The sun is in the middle here. This is the orbit of Mercury, the orbit of Venus, the orbit of the Earth, orbit of Mars. This is the asteroid belt, the main belt of asteroids, and up here is Jupiter.
And then,
And this is a picture of where all the asteroids are at a certain point in time. It says that this is December 6, 2009. So this is today.
there we go.
There we are. I didn't notice that. Okay, so this is where all the asteroids are that are dangerous. That are the ones that people worry about. And as you can see that in the area of the Earth, that's quite a number that are close. Some of them are above the orbit, below the Earth's orbit. That's Paul was enjoying it, yeah. And Steve already told that the number of observations very rapidly increased and the accuracy of the orbit rapidly increased. This was the orbit that was ultimately calculated. So here's the Sun again. It's the orbit of the Earth. It's the orbit of Mars. And the asteroid 2008 TC3 moved just outside of Mars orbit, coming in like this, just inside of Earth's orbit. So it had an orbit like this. And when it finally hit the Earth, it hit it here. And what Paul did was he calculated the orbit back in time to see how far, with the precision we have, this is only 20 hours of observing, how far could we calculate the orbit back in time so that it's still well defined, that you know where the object is. And that is only until 1961, sort of over the range of my life, is when you can integrate this asteroid back in time. Because in 1961, the asteroid passed at 0.18 astronomical units from the Earth with an error bar of 0.12. So it could have been coming very close to the Earth back in 1961. And the problem then is that if you go further back than 61, then you have to have a Monte Carlo type approach, which means that you, instead of calculating one orbit back, you calculate thousands of orbits back, all within the range of uncertainty. And that's what he did. So he basically started out with all these different asteroids that now are all sort of at the position where you expect a TC3 to be. I guess this is in 1961. Yeah, this is 1961. So the asteroid was somewhere in 61, was somewhere along this line. It could have been coming very close to the Earth, but it could also have been quite far away. So he then takes all these orbits and then he calculates that back in time. And then if you go 5,000 years back, this is all the positions where 2008 TC3 could have been. So it's still pretty much the same orbit. So the orbit is very stable. And I thought that might be nice to show. And then this is something that the next presentation will be about. This is the orbit of 2008 TC3. And this is the orbit of another F-class asteroid, 1998 KU2, that we think could be sort of the trail of crumbs. These things could be from the same debris field in the asteroid belt. So I thought that was nice to show you. I'm glad that Paul made the effort to make the presentation. And let me now give the word to François Collin from the IMCC in Paris, France.
Selection event in Paris Observatory. So I will speak of dynamic. So this job was made by Jeremy Robaillon, but it used the software we developed to make prediction of meteor showers. So it's quite the same. You will see, especially when we compute many orbits with the Monte Carlo method. So the basic idea, the goal, in fact, of our work, of this work, is to understand the evolution of 2008 TC3, and to understand in the past where it can be and where is the parent body of the Euroid, because we know it's the Euroid and it's a long story about the parent body Euroid. I think Peter will speak a lot about that after, about the F family on the asteroid. And so the idea is to see where can be this asteroid at a long time ago, and is it possible to find the parent body of this meteorite. Okay. So just an introduction on dynamics. And after the method to explore the dynamics of 2008 TC3 and the results, and the link between the F-type asteroid. And you saw also in the film this morning on the link with 1988. Okay. Thank you. Oops. So 2008 TC3 is found to be a F-type asteroid, so we have about the shape you see this morning also, about when you make spectroscopic study of the asteroid, you have the type of F type asteroid. So it is known that Ureid does not perhaps came from the F-type family. So F-type is a strange family because it's a very old family. So it's not really a dynamical family, because for dynamical family generally they are younger than this, and so it's easy to understand because we know that sometimes they are together, so we can go back to the shock who produced the family. And here it's very difficult because it's very old, and in fact, as it's so old, it all is blurred. Like you can't go back so easily in the past, especially at the beginning of the solar system. So in fact, we find that one asteroid, the idea is to find an asteroid that is similar to 2008 DC3, and so the only asteroids that are similar are near-Earth asteroids, so there are not so much near-Earth asteroids. We know about 6,000 NEOs. So we found that 1998 U2 as about could be the parent body, or it is not the parent body. It could be a brother of 2008 TC3. So it's a larger asteroid, and you see that you have a high semi-axis, so it's 2.2 AU, as 2008 TC3 it's only 1.2 AU. But in fact, it can cross the Earth's orbit at the same place. So it's very. The only difference is the difference with the semi-axis. So the idea to, as say Peter, is to really use a interferometer, because it's impossible to go back in the history when there's very short flyby of the Earth, because a small uncertainty on the position give after a lot of uncertainty. So we have to explore all the space of many objects and to go back to make the integration. So in fact the problem here is more of a CPU time, because it costs a lot of CPU time to make this kind of work. So we only use 1,000 clone objects. So clone objects are objects where we change slightly the orbit within the uncertainty you saw just before. But here we go back until 100,000 years, so a lot more than Paul showed us work, and we can see what's happened. So you show the time. So it goes. Can we start? So you see on the right 2008 TC3, and on the left, on the right, the asteroid, the other one, and you see the time spreading at the same speed. One more time. Okay. So you have the axis, here the axis is the semi-axis of the orbit, and the other axis is the eccentricity. So you see that at the beginning it was of course close to 1 point, and with the time it spread over this orbit. And this orbit is still a distance, a periodic distance for a periodic distance equal to 1, so all these orbits are close to the Earth.
So I
Yes.
need to, I don't get it.
Yes, yes, sure.
So those are, the left is 2008 TC3,
Yes,
and what's on the right?
that's
The other one, the other
the
asteroid.
other one, yes.
But their elements don't intersect ever. I was
I will show you after.
expecting them to intersect.
I will show you. If we go. Just some of them.
Just the next slide.
Just next.
Oh, it's the video icon.
Yes, yes. Okay.
So in fact here it's more understandable because you have the two graphics on the same one. So you see here is 2008 TC3. So you see at the beginning it is here, and you see it spread along this line. So this line is all the asteroid we have a distance to the Sun equal to 1 year. So they are all near asteroid. And the other is one is here, and you see it spread like this. What said Peter just before is that the orbit is quite stable, and that's it's amazing because generally this area of the solar system is quite chaotic. So generally the lifetime of a near-Earth asteroid is less than 100,000 years, and here it's quite stable, but you have some encounters with the Earth. And so these encounters of the Earth are here, and they spread a little more the cloud of points. And here also you have encounter of the Earth with the other asteroid. So at the end, you see that it seems only 100,000 years, but it seems quite obvious that in 200,000 years you can have an evolution of an asteroid like this, the basic one, to an orbit like 2008 TC3. So it's clear that we need more time, more objects, because here we have just two objects, but here for the two objects in the Monte Carlo simulation we are good. So it's clearly not enough. But it seems that if we have more objects, and if we can integrate on a more long time, it will be good to. This object can be a source of this. So in fact, we just need CPU. I think we are the only one who don't need more rocks. Okay. So here you have, so this is the same diagram. So we don't, here you see all the asteroids, so you see the Khartoum gaps. You see how, here you see also the semi-axis, and here is also the eccentricity. So you have here all the main belt, and you have also, this is the Earth's orbit, it's 1 EU, and you see here the candidate parent body is here, and in fact, all the objects spread like this on this orbit. So how it can spread? It spread mainly with the Yarkovsky effect. So probably you don't know what is Yarkovsky effect, but it's a very small effect, and it's due to thermal effect. So the idea is very simple. For example, on the Earth, you know that it's on a typical day, the temperature is higher in around 3 or 4 in the afternoon, and not at noon when the sun is at the top. And the idea is that just with the thermic inertia, there is a difference with this maximum temperature. So for an typical asteroid is the same. So there's a force which is always in the same way, which is called Yarkovsky effect. So it's very faint, and we don't know this for a long time. But it's very faint, but it's very constant. And so this force can make move the orbits, and that can make evolve the orbit. And now we know that it's a major effect for introducing asteroids